Andromeda is called our nearest large galactic neighbour, but its light still needs 2.5 million years to reach Earth. That is the strange calm of the universe. The closest great island beyond the Milky Way is already separated from us by a distance almost impossible to feel. Between galaxies, matter becomes so thin that whole cubic meters of space may hold only a few particles, while expansion slowly stretches the gaps even farther. If this kind of quiet science journey helps you relax, think, or drift towards sleep, a like, a subscription, or a share helps calm space science keep creating thoughtful explorations like this. Thank you for spending your time here and watching with us. Share in the comments where you're watching or listening from, what time it is there, and whether this is part of your night, study, work, or rest. From the familiar stars above Earth, the story now moves outward into the true distance between galaxies. Every star visible to unaided human eyes belongs to the Milky Way. This single fact gives the familiar night sky a limit that is easy to miss. The stars appear scattered across darkness as if they were openings into the wider universe, but they are all local in the galactic sense. The bright stars that define the constellations, the pale band of the Milky Way crossing a dark sky, the faint stellar points that become visible far from city lights, all of them sit inside the same galaxy as the Sun. None of the ordinary stars seen without a telescope is a separate galaxy. None is part of the deep cosmic web beyond the Milky Way. The visible sky begins with intimacy, even when it feels enormous, because human eyes see only a small portion of the structure that already surrounds them. The Milky Way is not a small object. It is a spiral galaxy roughly 100,000 light-years across, containing somewhere between 200 billion and 400 billion stars, along with gas, dust, stellar remnants, star clusters, dark matter, and a central region dense enough to alter the motion of everything around it. Light, the fastest signal in nature, would need about 100,000 years to cross the bright stellar disk from one side to the other. That measurement alone exceeds the scale of human history. When the earliest known cities were still far in the future, light crossing the full width of the Milky Way would still have been in the middle of its journey. Yet this enormous structure is only the starting point. It is the local environment, the immediate home system, the region within which every familiar star is contained. The difficulty begins because the mind tends to treat a galaxy as if it were already the largest meaningful unit. In ordinary speech, the word galaxy can feel complete, as though it marks the end of scale. But in astronomy, it is closer to the first large step. The Milky Way is immense when measured against planets, star systems, and human travel. Against intergalactic distance, it becomes a measuring unit rather than a final scale. That shift is the beginning of the real problem. To understand the space between galaxies, the Milky Way first has to be understood not as a full universe of its own, but as one galaxy among many. One structured concentration of matter inside a much larger arrangement. The Sun lies about 26,000 light-years from the galactic centre, in a relatively quiet region of the disk. It orbits the centre of the Milky Way at a speed of roughly 500,000 miles per hour. Yet even at that speed, one full orbit takes around 230 million years. This long circuit is sometimes called a galactic year. Since complex animals became common in Earth's oceans, the solar system has completed only a few such circuits. Since the first dinosaurs appeared, it has completed roughly one. The motion is real, but the scale makes it slow beyond ordinary experience. The Sun is not fixed in the galaxy. Earth is not fixed around the Sun. The entire local system is moving through a disk of stars, orbiting a centre hidden from ordinary sight by thick lanes of dust and gas. From within the galaxy, the Milky Way cannot be seen as a whole. Its spiral shape has to be inferred from radio observations, star counts, gas motions, infrared surveys, and comparison with other galaxies. This matters because the first lesson of galactic scale is not distance to another galaxy. It is the fact that even the home galaxy cannot be viewed directly from the outside. The human point of observation is embedded within the thing being measured. The bright band of the Milky Way is not a view of the galaxy from a distance. It is a view through the crowded plane of the disk, where stars, dust clouds, and glowing gas overlap along long lines of sight. The galaxy is so large that the view from inside it is partial by nature. Its full form has to be reconstructed, not simply seen. That alone gives a quieter but more accurate sense of its size. A structure too large to be looked at from outside, too wide for light to cross in less than 100,000 years, and too complex to map without multiple kinds of observation is still only the nearest layer of cosmic distance. The stars within it are separated by large gaps, but those gaps are small compared with what lies beyond the galactic halo. The nearest star system to the Sun is more than 4 light-years away. That is already a severe distance. A spacecraft built by human beings would need many thousands of years to reach it using present technology. Yet within the Milky Way, such distances are normal. Stars are separated by light-years, but they are still part of the same shared gravitational structure. Their motions are shaped by the combined mass of the galaxy. Their chemical histories are connected through cycles of star formation, supernova enrichment, and gas recycling. The space between stars is thin, but it is not empty in the broader galactic sense. It contains diffuse gas, dust grains, magnetic fields, radiation, and the remnants of older stellar processes. It also contains the raw material from which new stars may form. In this way, the Milky Way is not simply a collection of isolated stars. It is an active system, with internal circulation and a long memory of formation, destruction, and renewal. The familiar sky hides that system because individual stars appear as points. Their depth is lost to the eye. A nearby bright star and a much more distant luminous star can appear close together in a constellation, even though they have no physical relation to each other. The patterns assigned to the sky are mostly visual alignments from one location inside the galaxy. They are not real groupings in three-dimensional space. This is another place where intuition fails gently but completely. The sky makes depth collapse into a surface. Astronomy has to restore that depth by measurement. Once depth is restored, even the local sky becomes less simple. The bright star in one constellation may be tens of light years away. Another may be hundreds, another thousands. They appear together only because the view from Earth compresses different distances into a single dark field. The galaxy is therefore not only large, it is difficult to perceive honestly from within. The mind sees a ceiling of stars, but the measurements reveal an extended stellar system with a diameter large enough that events on one side can remain causally distant from the other for spans longer than recorded civilization by many orders of magnitude. This is the first correction needed before the distances between galaxies can be approached. The Milky Way is not the whole sky, it is the foreground. Beyond it are other galaxies, each with its own stars, gas, dust, black holes, clusters, and dark matter halo. Some are small dwarf galaxies with only a fraction of the Milky Way's mass. Others are vast elliptical systems containing many more stars than the Milky Way. Many are so distant that their light began travelling before Earth had mammals, forests, or even a stable oxygen-rich atmosphere, depending on the object being observed. But the first step beyond the Milky Way is not to the most distant galaxies. It is to the nearest large one, Andromeda. That distance is about 2.5 million light-years. The number is often repeated but repetition can make it feel smaller rather than larger. It becomes a label. The scale disappears behind familiarity. To recover its meaning, the size of the Milky Way has to remain in view. A galaxy 100,000 light-years across is already too large for direct human intuition. The distance to Andromeda is about 25 times that diameter, even after accepting the vastness of the home galaxy. The nearest large neighbouring galaxy still lies far beyond it, across a gap that would swallow the Milky Way many times over. That is the point at which the familiar sky begins to lose its comfort. The stars overhead are not signs that the universe is densely filled at all scales. They are signs of being located inside a rare concentration of matter. The ordinary night sky is bright only because Earth is inside a galaxy. It gives a local impression of abundance. The wider universe is not arranged that way. Most of its volume is not filled with stars. Most of it is not filled with galaxies. The visible points of light belong to places where matter has gathered, while the spaces between those gathered regions are far larger and far thinner. The Milky Way makes the universe seem closer than it is. It surrounds the solar system with stars and gives the impression that cosmic distance is a gradual extension of the same pattern. But the edge of a galaxy is not followed by another similar field of stars. It is followed by a vast decline in density, then by intergalactic space, then only after millions of light-years by another galaxy. This is why the first section of scale must remain inside the Milky Way. The galaxy is large enough to overwhelm ordinary measurement, yet small enough to be only the beginning. It holds every familiar star, but it does not define the true spacing of the universe. It gives the human eye a luminous neighbourhood, while concealing the far greater emptiness beyond that neighbourhood's edge. Before Andromeda can be understood as nearby, the Milky Way has to be understood as already immense. Before intergalactic distance can be felt as severe, the home galaxy has to be reduced from an apparent universe to a single object. That reduction is not diminishing, it is clarifying. It shows that the first lost foothold is not at the edge of the observable universe, or even at the boundary of the local group. It begins much closer, with the realization that everything visible in the ordinary starry sky is still only the near side of cosmic scale, and that the real distance between galaxies begins only after that familiar brightness has ended. Andromeda is often described as the nearest large galaxy to the Milky Way, but that description can make the distance sound gentler than it is. Nearness at this scale does not mean closeness in any ordinary sense. It means that among the great galaxies scattered through the local universe, Andromeda is the first major one beyond the Milky Way's own system. Its light reaches Earth from a distance of about 2.5 million light-years. That number is familiar in astronomy, yet its familiarity can weaken its force. A light-year is not a unit of time, but a unit of distance. The span light crosses in 1 year while moving at about 186,000 miles each second. In a single year, light travels nearly 6 trillion miles. Andromeda is not 1 light-year away, or 1,000, or 100,000. It is about 2.5 million light-years away, and the light seen from it began travelling long before modern humans existed. When that light left Andromeda, Earth was in an earlier stage of its own biological history. The ancestors of human beings were present, but the species that would later build telescopes, measure spectra, and name galaxies had not yet appeared. Andromeda was already a mature galaxy then, filled with old stars, star-forming regions, dust lanes, stellar remnants, globular clusters, and a central mass shaped by long gravitational history. The light now arriving from it is a delayed physical message from a galaxy, as it was millions of years ago. This time delay is not a flaw in observation, it is built into astronomy. Every distant object is seen through travel time. and Andromeda is close enough to be a neighbour, while still far enough to make the present unreachable by sight. Andromeda is faint to unaided eyes, even though it contains roughly 1 trillion stars. Under dark skies, it appears as a small, pale patch rather than a grand spiral, because distance reduces even a galaxy to a soft blur. Its true size on the sky is larger than the full moon several times over, but most of that light is too diffuse to stand out clearly against the darkness. The human eye catches only the brighter central region. Telescopes and long exposure images reveal more of its structure, including the broad disk, dark dust lanes, satellite galaxies, and extended halo. This difference between appearance and reality is important. Andromeda is not small because it looks small. It looks small because the gap is so large that a galaxy wider than the Milky Way is reduced to a faint oval of light. Distance is doing almost all the work. If Andromeda were bright enough for the full extent of its disk to appear easily in the night sky, it would stretch across a broad region of the sky, making its physical size more apparent. But its light is spread thinly across the field of view, and so the nearest large galaxy remains easy to overlook. The scale becomes clearer when the Milky Way is used as the measuring unit. The bright disk of the Milky Way is about 100,000 light-years across. The distance to Andromeda is about 25 times that width. This is not a small gap between neighbouring systems. It is a gulf large enough that the entire home galaxy becomes a repeated measure inside it. The Milky Way and Andromeda are often spoken of together because they dominate the local group, the small collection of galaxies bound by gravity in this part of the universe. That shared membership can create the impression that they are close companions. Gravitationally, they are connected. Spatially, they are separated by a distance that empties ordinary language of precision. The local group is real, but it is not crowded by human standards. It is a loose assembly in which the largest members are divided by millions of light-years, while smaller dwarf galaxies move around them like traces of earlier formation and capture. Between the Milky Way and Andromeda, there are not fields of stars like those within a spiral arm. There is not a continuous bridge of luminous matter. There are dwarf galaxies in the broader region, faint streams, dark matter halos, and very diffuse gas. But most of the volume between the two giant spirals contains almost no matter at all. This is the first severe lesson of intergalactic space. Galaxies may belong to the same gravitational group and still be separated by distances so large that almost everything familiar disappears between them. The gap is not only long, it is also extremely empty. A spacecraft travelling across it would not move from one star field into another in any gradual way. After leaving the extended region of the Milky Way, it would enter a space where nearby stars would no longer define the environment. The Milky Way would slowly contract behind it into a bright structure, while Andromeda would grow with almost immeasurable patience ahead. For most of the journey, neither galaxy would fill the surrounding space in the way the Milky Way fills Earth's night sky. The crossing would be dominated by distance itself, because there is little material in the gap to mark progress. Even at the speed of light, the journey would require millions of years, at any speed available to human spacecraft. The crossing is beyond practical mission planning by such a large margin that the phrase long journey is not useful. The distance is not merely difficult. It belongs to a category of scale where engineering imagination and astronomical measurement separate completely. Andromeda also shows that cosmic nearness can coexist with cosmic change. The Milky Way and Andromeda are moving toward each other under their mutual gravity. In several billion years, their outer halos will interact more strongly, and their stellar disks will begin a long merger process. This future collision is sometimes described dramatically, but the word collision can mislead. Stars inside galaxies are so widely spaced that direct impacts between individual stars will be rare. What will collide are the galaxies as gravitational systems. Their dark matter halos will overlap. Their gas will be disturbed. Their stellar orbits will be rearranged, and new waves of star formation may occur where gas is compressed. Over long time spans, the two spirals are expected to settle into a larger merged galaxy. This future does not make the current gap small. It shows that gravity acts across distances that ordinary motion cannot quickly close. Two galaxies can be falling together for billions of years and still remain millions of light years apart in the present. The approach is real, but it unfolds at a pace set by galactic mass and intergalactic distance, not by the shorter timescales familiar from planets or stars. The future merger also gives the Andromeda distance a second meaning. The gap is large enough to defeat present travel, but not large enough to free the galaxies from each other gravitationally. They are separated by a void and bound across it at the same time. That combination is one of the central facts of the local group. Space between galaxies is not always expansion winning in a simple way. In small bound systems, gravity can overcome the general expansion of the universe. The Milky Way and Andromeda do not recede from each other with the Hubble flow. They are close enough and massive enough for their mutual attraction to shape their future. This makes their distance scientifically useful. It is a reminder that the universe is not expanding by stretching every object away from every other object in the same simple pattern. Bound structures remain bound. Galaxies within groups can orbit, fall together, merge, and disturb one another while more distant galaxy clusters continue to separate with the expansion of space. Andromeda sits on that boundary in human understanding. It is near enough for gravity to matter directly, near enough to be visible without a telescope from dark skies, and near enough to be studied in detail. Yet it is still far enough that the light from its stars carries a delay older than the human species, and far enough that the Milky Way itself can be placed 25 times across the gap. This is why Andromeda is the right first step beyond the home galaxy. A more distant galaxy would be too abstract too quickly. Andromeda allows the scale to remain anchored while still becoming severe. It is part of the same local gravitational neighborhood. It shares a future with the Milky Way. Yet the space between the two is so wide that the nearest large galactic neighbor becomes a lesson in how sparse the universe really is. The distance does not need exaggeration. It only needs to be held in the right frame. A galaxy of immense size lies nearby by cosmic standards, visible as a faint patch under dark skies, moving slowly toward the Milky Way, destined to merge with it after billions of years. Between here and there are about 2.5 million light-years of mostly empty space. That is the closest large galaxy. The nearest major island beyond the Milky Way is already far enough that human intuition has no natural way to hold it. The Andromeda Gap is not the edge of cosmic scale. It is the first clear crossing beyond the local brightness, and it shows that even the nearest step into intergalactic space is already larger than the mind expects. The Milky Way becomes more useful as a measure only after its own scale is treated carefully. Its bright disk is often summarized as about 100,000 light-years across, but that single width hides several different structures layered together. There is the thin stellar disk, where most young stars, gas clouds, and spiral arms are found. There is a thicker disk of older stars, less bright and more widely dispersed. There is the central bulge, crowded with old stars and shaped by the long history of the galaxy. Around all of this extends a much larger halo, faint in visible light but important gravitationally. The halo contains old stars, globular clusters, streams of torn-apart satellite galaxies, hot gas, and a far larger dark matter component that cannot be seen directly. The Milky Way is therefore not just the bright band seen from Earth, or the spiral pattern shown in reconstructed images. It is a layered system whose visible part is only the clearest portion of a deeper gravitational structure. When the galaxy is used as a yardstick for the distance to Andromeda, the yardstick itself is not simple. It has edges that depend on what is being measured. The star-forming disk has one scale. The outer stellar halo has another. The dark matter halo reaches farther still. This is why galactic size is not always a single clean boundary. A planet has a surface. A star has a photosphere, the layer from which most visible light escapes. A galaxy fades outward gradually. Its stars become fewer. Its gas becomes thinner. Its satellite systems become more widely scattered. And its dark matter influence continues beyond the place where visible starlight becomes difficult to trace. The Milky Way's bright disk gives a practical diameter, but the galaxy's full influence extends much farther. Some halo stars and stellar streams reach hundreds of thousands of light-years from the centre. The dark matter halo may extend even farther, overlapping in a broad gravitational sense with the space where nearby dwarf galaxies move. This makes the space around the Milky Way less like a sharp border and more like a long transition from a dense stellar system into the thin environment of the local group. The inner disk is the most familiar region because it contains the Sun. It is also the region where the galaxy's structure is most actively maintained. Gas moves through the spiral arms, compressing in places where new stars form. Massive young stars heat surrounding gas and return enriched material to space when they die. Dust absorbs visible light and re-radiates energy at longer wavelengths. The spiral arms are not fixed solid bands of stars. They are regions where gas and stars respond to density patterns in the rotating disk. The Sun passes through this larger structure during its orbit around the galactic centre. But the timescale is so long that the motion has no obvious place in ordinary experience. It takes hundreds of millions of years for one full circuit. During that time, continents drift, climates shift, lineages rise and vanish, and the position of the solar system inside the galaxy changes only as part of a vast, slow-motion order. This local movement matters because the Milky Way is not a static object. It rotates, forms stars, absorbs smaller galaxies, and exchanges material between its disk, halo, and surroundings. Its present shape is the result of many older events. Some of the streams in its halo are the remains of dwarf galaxies pulled apart by tidal forces. Their stars no longer remain in compact systems, but their motions preserve traces of the galaxies they once belonged to. These faint streams help reveal that the Milky Way has grown through capture, as well as internal star formation. The halo is therefore a record of encounters. It is quiet compared with the bright star-forming disk, but it carries evidence of past mergers and long gravitational sorting. Globular clusters add another layer to that record. These compact spherical groups contain hundreds of thousands of old stars packed closely together. Many are nearly as old as the Milky Way itself, and some formed early enough to preserve information about conditions in the young galaxy. They orbit through the halo, often far above or below the galactic disk, marking a population that does not belong to the thin, bright plane of young stars. Seen at the scale of the Milky Way, even these clusters are small. Seen on their own terms, they are immense stellar systems. A single globular cluster can hold more stars than many small galaxies, yet in the Milky Way it becomes one of many orbiting relics. This nested scale is one reason galactic distances are difficult to feel. Structures that are enormous by one standard become minor features by the next. The same is true of the Milky Way's satellite galaxies. The Large Magellanic Cloud and the Small Magellanic Cloud are among the most prominent, visible from the southern hemisphere as detached patches of light. They are dwarf galaxies in the Milky Way's neighbourhood, close enough for their gas and stars to be affected by the larger galaxy's gravity. The Magellanic Clouds are not simply nearby objects. They are active systems undergoing tidal disturbance, with gas drawn out into a long structure called the Magellanic Stream. This stream extends across a large part of the sky in radio observations and shows how the influence of a large galaxy can reshape smaller companions across vast distances. Other dwarf galaxies surround the Milky Way more faintly, some with so few stars that they were found only through careful sky surveys. Their presence shows that the Milky Way is not alone even before the distance to Andromeda is considered. It sits inside a small retinue of smaller systems, some intact, some disrupted, all moving through the same broad gravitational environment. The central region of the Milky Way gives the yardstick another form of intensity. At the centre lies Sagittarius, a star, a supermassive black hole with a mass of about 4 million suns. It does not dominate the galaxy by swallowing everything around it. Its direct gravitational control is strongest near the centre. The wider rotation of the Milky Way depends on the total mass of stars, gas, and dark matter, not on the black hole alone. But Sagittarius A star is still a defining object because it marks the deepest central point of the galaxy and allows astronomers to test gravity under extreme conditions. Stars near it follow tight, fast orbits. By tracking those orbits over years, astronomers have measured the mass packed into the central region with remarkable precision. The black hole itself remains invisible, but the motion of nearby stars reveals it. More recently, the shadow region around it has been imaged by combining radio telescopes across Earth into a single planet-sized observing system. That image does not make the galactic centre ordinary. It shows how far measurement can reach inside a system whose centre is hidden from visible sight by dust. From Earth, the galactic centre lies in the direction of Sagittarius, behind dense clouds in the Milky Way's plane. Optical light is heavily blocked, so infrared, radio, and X-ray observations are needed to study it. The fact that the centre of the home galaxy requires indirect methods is itself a useful scale marker. Earth is not outside the system looking down. It is embedded in the disk, with dust and stars between it and the core. The galaxy must be reconstructed through methods suited to different wavelengths and different kinds of evidence. Neutral hydrogen maps trace gas. Infrared surveys penetrate dust to reveal older stars. Stellar motions show mass. Radio observations expose structures hidden from visible light. Each method adds a layer, and only together do they make the Milky Way coherent as a whole. When this full structure is held in view, the phrase "one Milky Way across" becomes heavier. It no longer refers only to a luminous disk drawn in a simple spiral shape. It refers to a wide rotating system with a hidden centre, a crowded bulge, spiral arms, gas clouds, dust lanes, star clusters, remnants, streams, satellites, a hot outer atmosphere, and an unseen dark matter halo. To cross it with light takes about 100,000 years if the bright disk is the chosen measure, and far longer if the outer halo is included. To cross 25 such disk widths, the approximate centre-to-centre distance from the Milky Way to Andromeda, means moving beyond not only the stars of one galaxy, but beyond the extended surroundings that make the galaxy a complete gravitational system. The distance between galaxies becomes severe because each galaxy is already a universe of structure by ordinary standards. The Milky Way is the ruler used to approach the next scale, but the ruler is itself so large that it cannot be seen whole, crossed quickly, or reduced to a sharp edge. That is what the galactic yardstick reveals. Before the void between galaxies can be measured honestly, the measuring unit has to be allowed its full weight. Beyond the outer regions of a galaxy, the character of space changes. The crowded disk gives way to a halo. The halo fades into a wider gravitational environment, and then the density of ordinary matter falls to levels that no place on Earth can reproduce in the same way. The space between galaxies is often called empty, but empty is only a first approximation. It contains matter, radiation, magnetic traces, and the long effects of gravity. What makes it difficult to understand is not the complete absence of everything, but the extreme thinness of what remains. Inside a galaxy, the space between stars may already be a very good vacuum by laboratory standards. It can contain only a few atoms in each cubic centimetre, sometimes more in gas clouds, sometimes far less in hot diffuse regions. Yet that thinness is still rich compared with the wider intergalactic medium. Between galaxies, ordinary matter is spread across such enormous volumes that the average density may fall to only a handful of particles in a cubic metre, and in the deepest voids it may be far lower. A cubic metre is a familiar human volume, close to the space occupied by a large appliance. In intergalactic space, such a volume may contain less matter than the smallest visible speck of dust by an unimaginable margin. The comparison does not need to be made dramatic. It is enough to state the physical condition plainly. Matter is present, but only barely. Most of the volume is not star, planet, dust cloud, or nebula. It is a plasma of rare particles, mainly hydrogen and helium, stretched through the spaces that separate galaxies and galaxy groups. Plasma means that some atoms have been stripped of electrons, leaving charged particles that respond to radiation and magnetic fields. In ordinary life, plasma is associated with heat and light. But the intergalactic medium is too diffuse to behave like a glowing gas in any visible way across most of its extent. It does not shine as a clear cloud. It does not make the gap between galaxies look filled. It is usually detected by the effects it has on light passing through it, or by faint emissions in special conditions near massive galaxy clusters. To unaided eyes, it would appear as darkness, not because nothing is there, but because what is there is too spread out to produce visible brightness. This distinction matters. The darkness between galaxies is not a solid backdrop or a container. It is a physical environment with density, temperature, motion, and history. Some of it is cold by cosmic standards. Some of it is warm or hot, especially where gravity has pulled gas toward filaments and clusters. Some of it has been enriched by heavier elements expelled from galaxies through supernova winds and active galactic nuclei. Most of it, however, remains close to the oldest chemical simplicity of the universe: hydrogen, helium, and small traces of heavier material. The same elements that formed early in cosmic history continue to occupy the larger spaces, although in forms too sparse to resemble any gas familiar on Earth. This is why the phrase near nothing is more accurate than absolute nothing. Intergalactic space is not a philosophical void. It is a very thin physical medium. It can be heated, shocked, ionized, compressed, and measured. It can slow radio waves by tiny amounts. It can absorb specific wavelengths from distant objects. It can trace the shape of the cosmic web. Its emptiness is real in terms of density, but not in terms of scientific meaning. A useful way to feel the scale is to remember that the air at sea level contains an enormous number of molecules in every breath. Those molecules collide constantly, transmitting sound, pressure, and heat in the intergalactic medium. Collisions between particles are rare because the particles are so far apart. A single proton may travel for a long time before encountering another particle directly. Temperature in such a medium can be misleading because temperature measures the average energy of particles, not how much heat a human body would feel. A region of intergalactic gas can have a very high temperature in the technical sense, because its particles move rapidly, while still containing so few particles that it would not deliver heat in the ordinary way. This is one of the quiet difficulties of cosmic environments. Words borrowed from everyday life continue to be useful, but only after their meanings are adjusted. Hot does not always mean warming. Empty does not always mean nothing. Dark does not always mean without radiation. The space between galaxies is filled with radiation, though most of it is faint, stretched, or outside visible light. The most important of these background radiations is the cosmic microwave background, the cooled afterglow from an early stage of the universe when light first began to travel freely through space. Today, it fills the universe in every direction with a temperature of about 2.7 degrees above absolute zero. It is not visible to human eyes because cosmic expansion has stretched its light into microwave wavelengths, yet it is present everywhere, passing through intergalactic space, through galaxies, through the solar system, and through Earth itself. It gives the universe a background glow that is almost perfectly uniform, with tiny variations that preserve information about early density differences. In the spaces between galaxies, where nearby starlight may be extremely weak, this ancient radiation remains one of the most universal features. It is not bright in the ordinary sense. It does not illuminate the void like sunlight on dust. It is a cold, diffuse field, detectable by instruments designed for microwave radiation. But its presence means that intergalactic space is never entirely without light. It contains the oldest light that can still be observed, diluted by expansion but not erased. Alongside that background are photons from stars and galaxies, spread thinly after crossing great distances. The combined light from all galaxies contributes to a faint extragalactic background, but it is weak compared with local sources when observed from within a galaxy. Far from any stellar system, the sky would not be crowded with nearby stars. Galaxies would appear as distant patches and points, and most directions would be dominated by darkness interrupted by faint signals. The cosmic microwave background would still fill the scene, but not in a way visible to biological eyes. Such a place would feel visually empty, yet physically it would remain part of the universe's record. The particles there have been affected by expansion. The radiation has been stretched by expansion. The distribution of matter has been shaped by gravity acting across billions of years. Even where almost nothing happens by ordinary standards, the history of the universe is still present in the conditions of the medium. The intergalactic medium also marks the difference between being inside a galaxy and being outside one, inside the Milky Way. The environment is shaped by the galaxy's internal processes. There are stars in every direction, though most are too faint or distant to see without instruments. There are molecular clouds where stars may form, remnants of stellar explosions, dust grains enriched by previous generations of stars, and magnetic fields woven through gas. Outside the galaxy, these structures thin away. Star formation becomes absent except in galaxies and their immediate surroundings. Dust becomes scarce. Heavy elements become more dilute. The dominant experience of space becomes separation. A galaxy is not simply an object floating in nothing. It is a region where matter has collected enough to produce stars, chemistry, planets, and complex structure. The intergalactic medium is what remains outside those collected regions. It is the low-density field from which galaxies once drew matter, into which they return some material, and through which their radiation travels. This gives the space between galaxies a quiet role in cosmic history. It is not merely distance. It is reservoir, record, and boundary. It holds much of the ordinary matter that is not locked inside stars and planets. It preserves traces of early chemical conditions. It receives material driven out from galaxies by energetic events. It helps define where galaxies end as visible systems and where their wider influence gives way to the general cosmic environment. The Milky Way and Andromeda are separated by millions of light-years of this kind of space. Not a perfect vacuum, not a bright bridge, not a simple absence, but a medium so thin that the word medium almost feels too substantial. The gap between galaxies is therefore more than a large number of light-years. It is a different physical regime. The rules remain the same laws of physics, but the conditions are far outside familiar experience. Density becomes almost negligible. Radiation becomes ancient and faint. Matter becomes difficult to detect directly. Distance becomes the main fact. When the bright structure of a galaxy is left behind, the universe does not become full in the same way again until another concentration of matter is reached. Between those concentrations lies the almost empty between, the largest environment by volume in the cosmos and one of the hardest to imagine plainly. Its importance comes from that plainness. It shows that the universe is not mostly made of luminous things. Even though luminous things are what first attract attention, it is mostly space, thin matter, faint radiation, and the gravitational pattern that connects them. The distance between galaxies feels severe because the crossing is not only long, it passes through a region where presence itself becomes sparse, where the usual markers of place nearly vanish, and where the faintest components carry the only evidence that the void is still part of the physical universe. The intergalactic medium becomes visible only when something else passes through it or disturbs it. By itself, most of this gas is too thin to shine in ordinary light. It does not form bright clouds across the space between galaxies, and it does not mark its presence with clear edges. For that reason, the study of intergalactic gas often begins with indirect evidence. Astronomers look for the effect of the medium on light, radio waves, and high-energy radiation. The method is careful rather than dramatic. A distant source sends radiation across a large section of the universe. On the way, that radiation meets diffuse material. The material changes the signal slightly. By measuring the change, the gas can be inferred. In this way, the emptiest regions of space become measurable not because they are bright, but because they are not perfectly absent. The first major clue comes from quasars, the intensely luminous centers of distant galaxies powered by matter falling towards supermassive black holes. A quasar can be bright enough to act as a background beacon across billions of light-years. Its light travels through intervening space before reaching telescopes near Earth. Along that route, it passes through many small concentrations of hydrogen gas distributed through the intergalactic medium. Each concentration absorbs light at particular wavelengths, depending on the atoms present and the motion of the gas. When astronomers spread the quasar light into a spectrum, those absorptions appear as many narrow dark features. The pattern is called the Lyman alpha forest. The name comes from a specific transition in neutral hydrogen, but the importance of the pattern is broader than the name. It shows that the space between galaxies is threaded with many separate layers and filaments of gas. A quasar spectrum is therefore not only a record of the quasar, it is also a record of the matter between the quasar and the observer. Each absorption feature marks gas at a different distance, because cosmic expansion shifts the wavelength according to how far the light has travelled. The forest becomes a depth map written into light. It does not show a picture in the ordinary sense, but it gives a measured sequence of intervening material, arranged along a line through cosmic space. With many quasars in different directions, astronomers can build a wider picture of how intergalactic gas is distributed. The gas is not uniform. It follows the same large-scale pattern as galaxies, becoming denser along filaments and thinner inside voids. This matters because it connects the nearly invisible medium to the visible architecture of the universe. galaxies reveal where matter has gathered enough to form stars. The Lyman alpha forest reveals the less condensed matter around and between them. The two records support the same general structure. A web shaped by gravity, with ordinary matter responding to an unseen dark matter framework. In this sense, quasar light turns the void into an archive. It allows the gas to be studied not only nearby, but across different eras, because more distant quasars look back to earlier stages of cosmic history. The forest changes with time. In the younger universe, intergalactic gas was denser because the universe itself was smaller. As expansion continued, the gas thinned, heated, cooled, and became ionized by radiation from early stars, galaxies, and black holes. The absorption record preserves traces of those changes. It is one of the reasons the space between galaxies is not simply an absence in modern cosmology. It is part of the evidence for how structure formed and how radiation changed the state of matter over cosmic time. A different view appears in galaxy clusters, where intergalactic gas is no longer as cold or as faint. Clusters are the densest large environments in the cosmic web. Hundreds or even thousands of galaxies move inside a shared gravitational field. But the galaxies are not the only important matter there. Between them lies a vast reservoir of extremely hot plasma called the intracluster medium. It can reach temperatures of tens of millions of degrees, not because it is dense like air or flame, but because gravity has pulled gas into the cluster and accelerated it until shocks and compression raise the energy of its particles. At these temperatures, the gas emits X-rays. Ordinary eyes would still see mostly darkness between the galaxies, but X-ray telescopes reveal a glowing volume spread across millions of light-years. In many rich clusters, this hot gas contains more ordinary matter than all the stars in the cluster galaxies combined. That fact changes the meaning of a cluster. It is not merely a collection of galaxies separated by empty space. It is a deep gravitational well filled with diffuse plasma, where the visible galaxies are only the brightest concentrated parts of a larger system. X-ray observations also show how active the spaces between galaxies can be. Jets from supermassive black holes push cavities into the hot gas. Shock waves move outward through the plasma. Cooling gas can sink toward cluster centers, while energy from active galactic nuclei can slow that cooling and regulate star formation. These processes happen at scales far larger than any single galaxy, yet they influence the development of galaxies inside the cluster. The invisible medium is therefore not passive. Under the right conditions, it stores energy, carries disturbances, and helps control how galaxies evolve. The same broad lesson appears from another modern tool, fast radio bursts. These are brief pulses of radio waves from distant cosmic sources. Many last only milliseconds, but they can be detected across enormous distances. Their exact origins are still being studied, with some link to highly magnetized neutron stars. But their usefulness for intergalactic gas comes from what happens during travel. Radio waves moving through plasma do not all arrive at exactly the same time. Lower frequency waves are delayed slightly more than higher frequency waves. The amount of delay depends on the number of free electrons encountered along the path. This spreading of arrival times is called dispersion. By measuring it, astronomers can estimate how much ionized material the burst passed through between its source and Earth. A fast radio burst is therefore a probe fired naturally across intergalactic space. It carries an imprint of the medium in the timing of its signal. This has become especially important because cosmologists long knew that a large fraction of ordinary matter was missing from direct inventories of stars, galaxies, and easily observed gas. The missing matter was not dark matter. It was made of ordinary particles, mainly protons and electrons. Expected from early universe measurements, but difficult to locate in the present universe because it was spread too thinly and too warmly between galaxies. Fast radio bursts have helped confirm that much of this matter resides in diffuse intergalactic plasma. The delay in their signals matches the amount of material that should be present across long cosmic paths. The result is quiet but significant. Matter that seemed absent was not absent. It was distributed through the spaces that had looked nearly empty. This changes the emotional scale of the void without changing its physical thinness. The intergalactic medium remains extraordinarily sparse, but it contains a large share of the universe's ordinary matter because the volume it occupies is enormous. A very low density spread through a vast enough region can add up to a major reservoir. The challenge is that such matter rarely announces itself directly. It must be found through absorption, emission, timing delays, and gravitational consistency. Each method sees a different state of the medium. Quasar absorption detects cooler or moderately ionized hydrogen along the line of sight. X-rays reveal very hot gas in massive clusters. Fast radio bursts count free electrons through dispersion. Ultraviolet observations trace warmer gas containing heavier elements, showing where galaxies have enriched their surroundings. Together, these methods turn the empty-looking space between galaxies into a layered physical system. None of them removes the severity of the distance. Instead, they make the distance more exact. The gulf between galaxies is not a blank region beyond measurement. It is a region whose contents are so faint that the universe itself has to provide the measuring instruments a quasar behind it, a cluster deep enough to heat it, a radio burst crossing it, a spectrum sensitive enough to record what it absorbed. The void leaves fingerprints only when light and matter meet across immense spans. That is why intergalactic distance can be known in more than one way. It is measured not only by how far apart galaxies are, but by what their separation does to radiation travelling through the space between them. The emptiness has texture, but the texture is subtle. It must be read from shadows in spectra, from delays in radio pulses, from X-ray glow around clusters, and from the missing matter that reappears when the right signals are examined. What emerges is a calmer and more difficult picture than simple darkness. Between galaxies there is space so thin that ordinary intuition cannot enter it, yet across that thinness lie records of gravity, heat, radiation, and cosmic history. The void does not speak loudly. It modifies passing light by small amounts, and from those small changes the largest spaces in the universe begin to become legible. The large-scale structure of the universe begins with a small unevenness. In the earliest observable record, matter is not arranged in finished galaxies, clusters, and voids. It is a hot, dense, expanding mixture whose density is nearly the same everywhere, but not perfectly the same. Tiny differences exist from place to place. Some regions contain slightly more matter than average, others contain slightly less. The differences are extremely small, but they matter because gravity does not need a large beginning to create a large outcome. A region that is a little denser pulls on its surroundings a little more strongly. Material falls toward it, making it denser still. A region that begins slightly emptier loses matter to its denser neighbours and becomes emptier over time. This slow amplification is one of the central processes behind the cosmic web. The web is not an image added to the universe from outside. It is the natural result of expansion, gravity, ordinary matter, radiation, and dark matter evolving together across billions of years. The earliest map of those initial unevennesses comes from the cosmic microwave background, the ancient radiation released when the universe cooled enough for light to move freely. Its temperature is almost uniform across the sky, but careful measurements show slight variations. Those variations mark regions of slightly different density in the young universe. They are the faint starting pattern from which later structure developed. In that early state, ordinary matter was still strongly affected by radiation, while dark matter had already begun to gather under its own gravity. Dark matter is known through its gravitational effects rather than through emitted light. It does not shine, absorb, or reflect in any ordinary way, but it contributes most of the matter in the universe. Because it interacts weakly with radiation, it could begin forming gravitational wells before ordinary gas was fully free to collapse. Once the universe cooled further, ordinary matter fell into those wells, gas collected where dark matter had already made deeper gravitational paths. Over time, that gas cooled in the densest regions, formed the first stars, and later assembled into galaxies. This sequence is important because it means visible galaxies are not the original framework. They are the luminous outcome of a deeper structure that was already taking shape before stars existed. The cosmic web is therefore traced by galaxies, but it is not made only of galaxies. It includes dark matter, diffuse gas, clusters, filaments, sheets, and voids. Galaxies are the bright markers placed along a larger gravitational arrangement. When galaxy surveys map millions of objects across the sky, the pattern that appears is not random. Galaxies gather along long filaments and broad walls. They are concentrated at intersections where many streams of matter meet. Between those concentrations are vast low-density regions called cosmic voids. These voids are not small, empty patches inside a crowded universe. By volume, they are the dominant environments. Most of cosmic space lies in voids, where galaxies are rare and the intergalactic medium is extremely thin. The filaments and clusters are important because they hold much of the visible structure, but they occupy only a smaller fraction of the total volume. This is one of the clearest ways in which appearance can mislead. Telescopes naturally draw attention to luminous matter. The eye follows galaxies because they shine, but the architecture of the universe is defined just as strongly by where galaxies are not. The distances between filaments and clusters can be enormous because gravity has moved matter out of underdense regions and into denser ones. A void grows emptier not because matter disappears, but because matter drains away over cosmic time. Expansion stretches the region while gravity draws material toward its boundaries. The result is a universe in which structure is concentrated along surfaces and strands surrounding large interiors of rare matter. This is not a metaphor in the scientific sense. It is the measured distribution of matter on the largest scales, seen through redshift surveys, gravitational studies, gas absorption, and the pattern left by early universe sound waves. The same general spacing appears in different kinds of data, which is why the cosmic web is treated as a physical structure rather than a visual impression. Its filaments can extend for hundreds of millions of light-years. Its clusters can contain hundreds or thousands of galaxies bound in a shared gravitational field. Its voids can span tens or hundreds of millions of light-years, and some known under dense regions are larger still. Each scale makes the gap between the Milky Way and Andromeda seem local. The Andromeda distance is severe to human intuition, but it belongs to a small bound group. The cosmic web introduces separations between whole systems of galaxies, between clusters, superclusters, and void boundaries. Here the universe is no longer being measured by the distance from one galaxy to another nearby galaxy. It is being measured by the spacing of the largest organized features that gravity has had time to build. At these scales, a galaxy becomes a point in a survey, not because it is small in itself, but because the structure being mapped is so much larger. A spiral galaxy 100,000 light-years wide can vanish into a dot when placed inside a filament hundreds of millions of light-years long. That change in scale is not only mathematical, it changes the meaning of location. A galaxy inside a dense filament has a different environment from a galaxy inside a void. A galaxy falling into a cluster enters hot gas, stronger tidal fields, and repeated interactions. A galaxy in a quiet low-density region may continue forming stars with fewer disturbances. The cosmic web is therefore not only a distribution of objects, it is an environmental system that affects the histories of the galaxies within it. The web also preserves information about the universe before galaxies formed. In the early hot plasma, pressure waves moved through matter and radiation. When the universe cooled and light separated from matter, those waves left a preferred scale in the distribution of material. This imprint is called baryon acoustic oscillation. It can still be measured in the spacing of galaxies across vast distances. The idea is simple in outline, even though the measurement is precise. A process that occurred when the universe was young left a scale in matter, and that scale remains detectable billions of years later in the arrangement of galaxies. The distance between galaxies is therefore not only a present fact, it carries an ancient pattern. Some separations are shaped by local gravity, some by cluster formation, some by the widening of voids, and some by the original conditions of the early universe. The web is cumulative. It records the first unevenness, the growth of dark matter structure, the cooling of gas, the ignition of stars, the formation of galaxies, and the later movement of matter into clusters and filaments. This cumulative record also explains why the universe can look similar on the larger scales while still being richly structured on smaller ones. On scales of a few million light years, the distribution of matter can vary strongly. One region may contain a galaxy group, another a cluster, another a sparse void. On scales of hundreds of millions of light years and above, the universe becomes more statistically uniform. No region is expected to be the center. No direction contains a unique edge. The cosmic web has pattern without requiring a special location. That is a difficult balance for intuition, because ordinary experience often connects structure with a center or boundary. The large-scale universe has neither in any known observational sense. It has density variations, flows, and regions of greater and lesser concentration, but no privileged middle from which everything is arranged. The Milky Way is simply one galaxy in one small group, located in one part of a much larger web. This has a quiet consequence for the meaning of distance. The space between galaxies is not just empty separation placed between finished objects. It is the outcome of the same process that made the objects themselves. Galaxies exist because matter gathered. Voids exist because matter did not gather there, or because it was pulled away. Filaments exist because gravity drew material along the path set by early density structure. The emptiness and the brightness are related results, not separate facts. The cosmic web makes this connection visible at the largest scale. It shows that intergalactic distance is not accidental spacing. It has history, cause, and shape. The gaps are large because the universe expanded while gravity works slowly, drawing matter into some regions and leaving others increasingly thin. The filaments are long because small early differences were stretched and amplified. The clusters are dense because many streams of matter converged. The voids are vast because volume grew faster than matter could fill it evenly. By the time the web is fully recognized, the scale of the universe is no longer a simple collection of faraway galaxies. It becomes a connected pattern of concentration and absence, with ordinary galaxies marking only the most visible parts. The distance between galaxies begins to feel larger not because the numbers have changed, but because the numbers now belong to a structure whose main feature by volume is separation. Gravity remembers the early universe by gathering matter where the first unevenness allowed it to gather, and the spaces left between those gatherings became the largest regions the cosmos contains. The Milky Way does not sit in isolation, but its surroundings are still sparse compared with the richer parts of the cosmic web. Its immediate neighbourhood is the local group, a gravitationally bound collection of galaxies spread across roughly 10 million light-years. The name can sound modest, and in one sense it is. The local group is not a massive cluster. It does not contain thousands of large galaxies moving through a bright sea of hot gas. It is a smaller association dominated by two major spirals, the Milky Way and Andromeda, along with the Triangulum Galaxy and many dwarf galaxies. Most of its members are faint systems, some containing only a small fraction of the stars found in the Milky Way. Many orbit the larger galaxies as satellites. Others move through the group in wider paths shaped by the combined gravity of the whole system. The local group is therefore local only by the standards of cosmology. It is still a region so large that light needs millions of years to cross it, and so thinly populated that even its major galaxies are separated by distances far beyond ordinary scale. This neighbourhood gives the first complete form of the Milky Way's address. The Sun belongs to the Milky Way. The Milky Way belongs to the local group. The local group belongs to a broader flow of galaxies associated with the Virgo region and the wider nearby cosmic web. Each step outward changes what location means. Inside the solar system, location can be described by distance from the Sun. Inside the Milky Way, it can be described by position in the disk and distance from the galactic centre. Inside the local group, it is described by relationships among galaxies and their shared gravitational future. Beyond that, location becomes a question of motion through larger structures. Galaxies are not only placed in space, they are moving through it. Pulled by concentrations of mass and carried apart by cosmic expansion, where gravity has not bound them together. The nearest major galaxy cluster to the local group is the Virgo cluster, lying roughly 50 million light-years away. That distance is much larger than the width of the local group itself. Between the local group and Virgo, space is not completely empty, but it contains no continuous chain of large galaxies filling the gap in a dense way. The Virgo cluster is a very different environment from the local group. It contains well over 1,000 galaxies, including giant elliptical galaxies, many spirals, and numerous smaller systems. Its central region is dominated by massive ellipticals, especially Messier 87, a galaxy whose central black hole is one of the most studied in the nearby universe. The black hole in Messier 87 became famous because it was the first black hole shadow imaged by a global network of radio telescopes. That achievement depended on observing across an intergalactic distance so large that the galaxy itself appears as only one part of the Virgo cluster, yet close enough by cosmic standards for detailed study. Virgo matters not only because it is nearby, but because it is massive enough to affect the motion of surrounding galaxies and galaxy groups. The Milky Way and the local group are not falling directly into Virgo in a simple straight line, but their motion is influenced by the distribution of mass in that direction. Older maps often describe the Milky Way as part of the Virgo supercluster, a broader concentration of groups and clusters extending across about 100 million light-years. This term remains useful historically, but modern motion-based mapping has refined the picture. When astronomers study how galaxies deviate from the smooth expansion of the universe, they can trace the gravitational flows that reveal larger connected regions. Galaxies do not move only because space expands. They also have peculiar motions, meaning motions caused by local and regional gravitational pulls. By mapping those motions, astronomers can identify the basins toward which galaxies are drifting. In this view, the local group lies within a much larger region called Laniakea, a supercluster scale structure spanning roughly 500 million light-years. Laniakea contains around 100,000 galaxies, organized into many groups and clusters. The Milky Way sits not near its center, but toward its outer region. This position is important because it removes any sense that the home galaxy occupies a central or privileged location. The Milky Way is not at the center of the local group in any absolute sense, since the local group is dominated by a shared gravitational relationship with Andromeda. It is not at the center of the Virgo region. It is not at the center of Laniakea. It is one galaxy moving within a large flow pattern near the edge of a much wider structure. At the heart of the Laniakea flow lies a region associated with the Great Attractor, an area of unusually strong gravitational influence located roughly 200 million light-years away. The name sounds more dramatic than the measurement itself requires, but it reflects a real observational problem. For decades, astronomers saw that nearby galaxies, including the local group, were moving in a way that suggested a significant concentration of mass beyond the visible maps. The difficulty was that the direction of this mass concentration lies partly behind the plane of the Milky Way. Dust and stars in the galactic disk block visible light from that part of the sky, creating what astronomers call the zone of avoidance. It is not an empty zone. It is a zone where ordinary optical observation is obstructed by the foreground galaxy, radio, infrared. And X-ray observations can look through some of that obscuring material, revealing galaxy clusters and structures hidden behind the Milky Way's disk. The Great Attractor is not a single object. It is a complex region of mass, involving galaxy clusters and larger flows, and its influence is only part of a broader pattern. Beyond it lies the Shapley supercluster, one of the largest nearby concentrations of galaxies and galaxy clusters. It is farther away, but massive enough to contribute to the motion of galaxies across the local universe. This layered influence shows why a cosmic address cannot be reduced to one nested list alone. The Milky Way is in the local group, associated with Virgo, within the flow region called Laniakea, influenced by the Great Attractor and by even larger mass concentrations beyond it. These are not rigid boundaries like borders on a surface. They are gravitational relationships inferred from motion, density, and the distribution of matter. Some structures are bound strongly enough to remain together. Others are temporary or partial associations in a universe whose expansion becomes more important at greater distances. The result is a local universe that is both ordered and in motion. It has clusters, filaments, walls, voids, and flows, but not a simple set of fixed shells. This makes the space between galaxies more meaningful. The gaps are not merely the distances from one bright object to another. They are the spaces through which gravitational influence is expressed, through which galaxies move slowly toward denser regions or away with expansion, and through which the large-scale pattern can be measured. The local group itself is bound and will continue evolving internally, especially through the future merger of the Milky Way and Andromeda. Virgo, farther away, belongs to the nearby large-scale structure but is not part of the same small bound group. Laniakea describes a much wider flow, not a single compact object. Outside these regions, other superclusters and voids continue the pattern. The address grows less like a fixed place and more like a set of measured relationships. That is the quiet difficulty of locating anything in the universe. Position depends on scale. On one scale, Earth orbits the Sun. On another, the Sun orbits the center of the Milky Way. On another, the Milky Way moves within the local group. On another, the local group participates in a flow shaped by Virgo, the Great Attractor, and Shapley. Each layer is real, but none cancels the others. The full address is cumulative. It shows that home is not a stable point placed against a still background, but a moving part of a vast and uneven structure. The Milky Way sits near the edge of a large flow region, inside a universe where the brightest matter is arranged along filaments and clusters separated by enormous low-density spaces. This does not make the local environment exceptional in a mystical sense. It makes it measurable. The same laws that shape the motion of nearby satellite galaxies also connect the local group to mass concentrations hundreds of millions of light-years away. The distances are immense, but gravity gives them consequence. The local cosmic address is therefore not a simple statement of where the Milky Way is. It is a record of what surrounds it, what pulls on it, what it is bound to, and what lies too far away for binding to overcome expansion. At this scale, home is already on the edge of larger structures, and the next question is no longer only where the galaxies are. It is how the space between them changes while they are being measured. The distances between galaxies are not fixed distances in the way distances inside a room are fixed. They change because the universe itself is expanding. This does not mean that galaxies are flying outward from one central point into empty surroundings. There is no known central point of expansion inside the universe, and no observed outer surface into which galaxies are moving. The expansion is better understood as a change in the scale of space itself, on very large scales. The distance between unbound galaxies increases with time because the space separating them grows. Bound systems resist this effect. The solar system does not expand. The Milky Way does not expand. The local group remains held together by gravity. But beyond gravitationally bound regions, the expansion becomes the dominant motion. This is why the distance to a far galaxy is not only a measure of separation, it is also a measure of cosmic history. Light travelling from that galaxy crosses space while space is changing. By the time the light reaches observers near Earth, the galaxy that emitted it is usually farther away than it was when the light began its journey. This is one of the most important corrections to ordinary intuition. A light travel time and a present distance are not always the same thing. For nearby galaxies, the difference can be small enough that simple language remains useful. For very distant galaxies, the difference becomes large. A galaxy whose light has been travelling for more than 13 billion years is not simply 13 billion light-years away in the present configuration of the universe. During those 13 billion years, the space between that galaxy and the Milky Way has expanded. Its current distance can be tens of billions of light-years. This is why cosmologists use several kinds of distance, each suited to a different question. Look-back time describes how long the light has been travelling. Proper distance describes how far away an object is at a given moment in cosmic time, after accounting for expansion. Comoving distance uses coordinates that expand along with the universe, allowing the large-scale arrangement of galaxies to be described in a way that factors out the general stretching of space. These terms may sound technical, but they are needed because the universe does not provide one simple distance for every purpose. The answer depends on what is being measured: the age of the light, the current separation, the scale of structure, or the history of expansion. The observational sign of this expansion is redshift. When light travels through expanding space, its wavelength is stretched. Longer wavelengths correspond to redder light in the visible spectrum, though the same principle applies beyond visible colours as well. A distant galaxy has recognizable patterns in its spectrum, made by elements absorbing or emitting light at specific wavelengths. By comparing where those patterns appear with where they would appear in a laboratory, astronomers can measure how much the light has been stretched. The greater the redshift, the more the universe expanded while that light was travelling. This is not only a shift in colour, it is a measurement of the changing scale of space between emission and observation. In the 1920s, Edwin Hubble and others found that more distant galaxies generally show greater redshifts. This relationship revealed that the universe is expanding. The farther away a galaxy is, on average, the faster its distance from the Milky Way increases due to expansion. The rate of this expansion is described by the Hubble constant, although the exact value remains part of an active scientific tension. The basic discovery transformed cosmology because it showed that the universe is not a static arrangement of galaxies. It has a history. It was denser in the past. It is larger now. And its future depends on how expansion changes over time. The redshift of a galaxy therefore links distance with age. Looking farther away also means looking farther back, because light from more distant objects has taken longer to arrive. A galaxy observed at high redshift is seen as it was when the universe was younger. This makes telescopes into instruments of history as well as distance. The most distant galaxies observed by modern space telescopes are not seen in their present form. They are seen during early stages of galaxy formation, when the universe was only a small fraction of its current age. Their light began travelling before the Sun existed, before the Milky Way had its present form, and before many later generations of stars had enriched galaxies with heavier elements. Yet those galaxies, if they still exist in some evolved form, are now much farther away than the simple travel time of their light might suggest. Expansion has moved the current separation beyond the distance their ancient light crossed when it began. This can feel contradictory only because everyday distance is treated as stable. In cosmology, distance and time are linked by the changing scale of the universe. A photon can begin its journey when the source is closer, then spend billions of years crossing a universe that stretches during the passage. Some parts of the route expand while the light is already in transit. The photon still moves locally at the speed of light, but the total distance between source and observer changes along the way. At extreme distances, this leads to a result that can sound impossible if stated carelessly. Some galaxies are receding from the Milky Way faster than light because of the expansion of space. This does not violate relativity, because the galaxy is not moving through local space faster than light. Instead, the space between widely separated regions is increasing at a rate that, over enough distance, can exceed the distance light covers in the same time. Relativity limits motion through space. It does not impose the same simple limit on the growth of space between very distant objects in an expanding universe. The distinction is essential. Without it, the largest cosmic distances appear to conflict with the rules of physics. With it, they become a natural consequence of those rules applied to the whole universe. This is also why not every visible galaxy can remain visible forever. A galaxy may send light that reaches Earth today because it emitted that light when the conditions of expansion allowed the photon to make progress toward us. But light emitted by the same galaxy now, at a later stage of cosmic expansion, may never reach the Milky Way if the intervening space grows too quickly. The past light is observable, while the present light may be permanently beyond reach. The distance is not only large, it is changing in a way that alters what can ever be known. For objects near enough and gravitationally connected, such as Andromeda, expansion does not carry them away, their mutual gravity dominates. For distant galaxy clusters outside bound relationships, expansion rules their long-term separation. This scale dependence gives the universe a layered behavior. Locally, galaxies can fall together, orbit, and merge regionally. Groups and clusters can form larger associations and flow toward mass concentrations. At still greater distances, expansion separates structures that are not bound, and the separation grows with time. The same universe therefore contains both future mergers and permanent losses, depending on scale. The Milky Way and Andromeda will approach each other, while many far more distant galaxies will become less reachable with each passing era. This is not a contradiction. It is the balance between gravity and expansion. With gravity winning inside bound systems and expansion winning across the widest unbound spaces, The observable universe is shaped by this balance. Its radius is not simply the age of the universe multiplied by the speed of light, because space has expanded while light was travelling. The oldest light that can be detected, the cosmic microwave background, has been on its way for most of cosmic history. The matter that emitted it is now far beyond 13.8 billion light-years away in present distance, because the universe expanded enormously during the time the light crossed space. The observable universe, therefore, has a radius of about 46.5 billion light-years, even though the universe is about 13.8 billion years old. That larger radius is not an error. It is the direct result of expansion. It also means that the word observable has a precise limit. The observable universe is the region from which light has had time to reach the Milky Way since the early universe became transparent. Beyond that region may be more universe, perhaps much more, but its light has not reached this location and may never do so. Intergalactic distance, at this scale, becomes tied to the horizon of possible observation. The farther the source, the more its distance must be understood through expansion, redshift, and cosmic time. A number in light-years is no longer enough unless the kind of distance is specified. The universe refuses stillness not because every object is racing through space in a simple outward motion, but because the underlying scale of unbound space changes. Galaxies mark that change with their redshifts. Ancient light records it by arriving stretched. Present distances reveal it by exceeding simple travel times. The space between galaxies is therefore not a passive gap. It is part of the evolving structure of the universe, growing on the larger scales and carrying galaxies into futures that depend on whether gravity can still hold them together. Once expansion is included, distance stops being only a measure of how far away a galaxy is. It becomes a record of when its light began, how much the universe changed during the journey, and whether any future signal from that same place can ever arrive. The expansion of the universe would be easier to understand if it were slowing down. Gravity pulls matter toward matter, and for much of modern cosmology, it seemed reasonable to expect that the expansion begun in the early universe would gradually lose speed under the combined attraction of galaxies, gas, dark matter, and clusters. The universe might continue expanding forever, or it might eventually slow enough for a different fate. But the basic expectation was that gravity would act as a brake. In the late 1990s, observations of distant Type 1, a supernovae, changed that expectation. These supernovae are useful because their peak brightness can be calibrated, allowing astronomers to compare how bright they truly are with how bright they appear from Earth. That comparison gives distance. When two independent teams measured these distant explosions, they found that the supernovae were fainter than expected for a universe whose expansion was slowing in the usual way. The simplest interpretation was not that expansion had been braking too strongly, but that it had begun speeding up. The universe was not only expanding, its expansion was accelerating. This result was surprising because it required a dominant component of the universe that does not behave like ordinary matter. Matter becomes less dense as space expands, because the same particles are spread through a larger volume. Radiation also becomes diluted, and its wavelengths are stretched. But the cause of accelerated expansion appears to act differently. The name given to it is dark energy. The name is descriptive rather than explanatory. It does not identify a known substance in the ordinary sense. It marks the unknown influence responsible for the observed acceleration of cosmic expansion. In the current standard model of cosmology, dark energy makes up most of the total energy content of the universe, while dark matter and ordinary matter make up the rest. Ordinary matter, the material of stars, planets, gas, dust, and living bodies, is only a small fraction of the whole. This means that the distances between galaxies are governed mainly by something not directly seen in the galaxies themselves. On local scales, gravity still dominates. The Milky Way and Andromeda remain bound. Galaxy clusters hold together. Stars remain in galaxies, and planets remain around stars. But on the larger scales, where structures are not gravitationally bound, dark energy drives the acceleration that increases the separation between galaxy groups and clusters. The effect is not visible from day to day, or even across the span of recorded history. It belongs to cosmic time, yet its long-term consequence is severe. A galaxy cluster that is not bound to the local group will recede faster and faster as the space between grows. Its light will be stretched to longer wavelengths. Its apparent brightness will fade. Its future signals will take longer to arrive, then eventually no longer arrive at all. The key idea is the cosmic event horizon. This horizon is not a physical wall, and it is not the same as the edge of the observable universe today. It is a limit set by accelerated expansion. Beyond a certain distance, light emitted now from a galaxy will never reach the Milky Way, no matter how long time continues, because the space between expands too quickly for that light to make overall progress toward us. The photon still moves locally at the speed of light. Nothing strange happens to the photon in its own immediate region of space, but the total separation between source and observer grows in such a way that the journey can never be completed. This is one of the least intuitive facts in cosmology, because it separates visibility in the past from contact in the future. A galaxy can be visible as it was long ago, while its present light is already unable to reach us. The telescope receives an old message from a region whose current state has become permanently inaccessible. Over time, more galaxies cross this practical boundary for future observation. Their old light may continue arriving for a while, increasingly stretched and weakened, but the information becomes more delayed, more redshifted, and less connected to any present condition. This does not mean those galaxies disappear in their own locations. They continue to evolve. Their stars continue to age. Gas continues to cool or heat. Galaxies continue to merge inside their own bound groups, and black holes continue to grow or quiet down. The loss is not destruction. It is separation beyond causal contact. The universe becomes divided into regions that can no longer exchange signals. In a universe without accelerated expansion, enough time might allow light from more distant places to reach us, depending on the expansion history, with dark energy in its current form. The opposite occurs for many regions. The future visible universe becomes smaller in terms of what remains accessible, even though the total universe continues expanding. This future is gradual. There is no sudden darkening of the sky. Nearby stars remain. The Milky Way remains. Andromeda approaches. The local group continues its internal evolution over billions of years. The Milky Way and Andromeda will merge into a larger galaxy, along with other local group members. Star formation will continue where gas remains, then decline as gas is consumed, heated, or expelled. Far beyond this local system, however, distant galaxy groups and clusters will move away at increasing rates. Their light will shift farther into infrared, then radio wavelengths, and eventually become so stretched and faint that it carries no usable observational record for future astronomers. The sky seen from within the future merged local group will contain local stars and remnants, but the wider cosmic web will fade from view. The Virgo cluster, the Shapley concentration, and the far filaments beyond them will no longer be part of any observable map. They will still exist, but not within the reachable universe of that future location. This has a direct consequence for knowledge. The present era has access to evidence that will not always be available. The cosmic microwave background can still be measured, distant galaxies can still be observed across many stages of cosmic history. Redshifts still show expansion. Galaxy surveys still trace the cosmic web. Future observers living in the merged remnant of the local group may see a much emptier universe. If enough time passes, the evidence for expansion could become difficult or impossible to reconstruct from observation alone. Without visible distant galaxies, without a clear cosmic web beyond the local system, and with the ancient background radiation stretched beyond practical detectability, the universe could appear far smaller and more isolated than it really is. This is not because future science would be weaker in principle. It is because the universe would provide less evidence to measure. Cosmology depends on light that has had time to arrive. Accelerated expansion gradually removes sources from that exchange. The idea is sobering, but it is also scientifically clarifying. The distance between galaxies is not only a present measurement, it is part of a changing boundary between what can and cannot be known. Dark energy turns intergalactic space into a time-dependent limit. A distant galaxy is not merely far away. Its future visibility depends on whether light emitted later can still cross the growing separation. Many galaxies now seen in deep telescope images are already beyond any possibility of contact in their present state. They are part of the observable past, not the reachable future. The farther the object, the more strongly this distinction matters. At extreme distances, astronomy becomes a study of vanished access, not vanished objects, but vanished connection. This is why the phrase observable universe must be treated carefully. It does not mean the whole universe, and it does not mean everything that can ever be observed from this location. It means the region from which light has reached us by now, shaped by the age of the universe and its expansion history. The future observable region will not simply grow to include everything. Because of accelerated expansion, many currently visible sources will become unavailable for future observation. The horizon closes not by moving inward like a surface, but by allowing distant regions to recede beyond the reach of new light. The closing is slow, measured in billions upon billions of years, yet it is built into the same equations that describe the universe today. The largest distances are therefore not passive gaps waiting to be crossed. They are expanding separations with consequences for causality, observation, and memory. The local group remains a small pocket where gravity wins. Beyond it, more and more of the cosmic web belongs to a future from which no signal can return. The universe does not need to end for distance to become final. It only needs to keep expanding under the influence of dark energy. In that future, isolation is not caused by a boundary at the edge of space, but by the steady growth of space between unbound structures. The galaxies remain real, but their light no longer arrives. The record thins, the map empties, the horizon closes, and the universe slowly becomes unreachable to itself. The distance to another galaxy cannot be measured by sending a probe, waiting for a signal, or laying a single geometric line across space. The scale is too large, and the objects are too remote for direct contact to play any useful role. Astronomers measure the unreachable by building a chain of methods, each one extending the reach of the one below it. This chain is called the cosmic distance ladder. It begins with the nearest stars, where geometry still works, and it rises step by step until it reaches galaxies so distant that their light began travelling when the universe itself was young. The strength of the ladder is not that any one rung solves the whole problem. Its strength is that different methods overlap. A nearby method calibrates a farther method. The farther method then becomes useful beyond the range of the first. At each stage, uncertainty has to be carried carefully, because a small error in a lower rung can affect the scale above it. This is why distance measurement in astronomy is both powerful and delicate. It is not a matter of guessing how far a faint object might be. It is a layered system of comparison, calibration, and cross-checking, built over generations. The lowest rung is parallax. As Earth moves around the Sun, nearby stars appear to shift slightly against more distant background objects. The shift is tiny, but it is real, and it can be understood with simple geometry. A closer star shows a larger apparent shift. A more distant star shows a smaller one. By measuring the angle of that shift and knowing the size of Earth's orbit, astronomers can calculate the star's distance. This is the most direct method used beyond the solar system. It does not depend on how bright the star is or on assumptions about stellar behavior. It depends on a small change in apparent position caused by viewing the star from different places along Earth's orbit. Modern space observatories have made parallax measurements extraordinarily precise, especially within the Milky Way. They have mapped the positions and motions of vast numbers of stars, turning the local galaxy into a three-dimensional structure rather than a flat pattern on the sky. But parallax has a limit. As distance increases, the apparent shift becomes smaller until it falls below the ability of instruments to measure it reliably. The method that begins with geometry cannot simply be stretched to Andromeda or to distant clusters. A new rung is needed. That next rung depends on objects whose true brightness can be known. These are called standard candles. The idea is straightforward. If the real brightness of an object is known, and its apparent brightness from Earth is measured, the difference reveals its distance. A bright object nearby and a much brighter object far away can look similar in the sky. So the crucial step is knowing how luminous the object truly is. One of the most important standard candles is the Cepheid variable star. Cepheids expand and contract in a regular rhythm, causing their brightness to rise and fall. The period of that rhythm is tied to the star's true luminosity. A Cepheid with a longer pulsation period is intrinsically brighter than one with a shorter period. This relationship was identified by Henrietta Leavitt while studying variable stars in the Magellanic Clouds. Her insight gave astronomy a way to measure distances beyond the reach of parallax. Because many Cepheids in the same nearby galaxy were at roughly the same distance, their different apparent brightnesses could be connected to their pulsation periods. Once the relationship was calibrated, Cepheids became distance markers. By finding a Cepheid in a remote galaxy, measuring its pulsation period, and comparing true brightness with apparent brightness, astronomers could determine how far away that galaxy was. This method changed the scale of the universe. It allowed Edwin Hubble to show that Andromeda was not a nebula inside the Milky Way, but a separate galaxy far beyond it. That result expanded the known universe from one galaxy to a universe filled with galaxies. The ladder did not merely add a number, it changed the meaning of the sky. For even greater distances, Cepheids become too faint to detect clearly. The next major rung uses Type 1a supernovae. These explosions occur in systems involving white dwarf stars and can be calibrated because their light curves and peak brightness follow recognizable physical patterns. They are far brighter than Cepheids, bright enough to be seen across billions of light years. When such a supernova appears in a distant galaxy, its changing brightness can reveal its true luminosity, and its apparent faintness can reveal the distance. This method reaches far enough to measure the expansion history of the universe itself. It was through distant Type 1a supernovae that astronomers discovered the expansion is accelerating. Here the distance ladder does more than map space. It reveals the behavior of the universe over time. Each explosion is brief, but its light carries a measurement across a vast interval of cosmic history. Above these rungs, redshift becomes essential. A galaxy's spectrum contains lines produced by known atoms and ions. When the universe expands while light travels, Those lines shift toward longer wavelengths. Measuring the shift gives the redshift, and redshift connects the galaxy to the expansion history of the universe. For nearby galaxies, redshift can be affected by local motions, because gravity pulls galaxies within groups and clusters. For distant galaxies, the expansion signal becomes dominant. Redshift is therefore not a simple ruler by itself. It must be interpreted through a cosmological model that describes how space has expanded over time. When that model is constrained by many kinds of evidence, redshift becomes a powerful way to estimate distances across the observable universe. It allows astronomers to place ancient galaxies in cosmic time, not only asking how far away they are now, but how old the universe was when their light was emitted. A high redshift galaxy is therefore both remote and early. Its distance is spatial, but its light is historical. There are also rulers built into the universe itself. One of them comes from baryon acoustic oscillations, a pattern left by pressure waves in the early hot universe. Before atoms formed, ordinary matter and radiation were coupled together, and waves moved through that dense plasma. When the universe cooled enough for light to travel freely, those waves left a preferred scale in the distribution of matter. Billions of years later, that scale can still be detected statistically in the spacing of galaxies. It is not a ruler made from one object, but from the pattern of many objects across immense volumes. By measuring that pattern at different redshifts, astronomers can test the expansion history of the universe independently of the traditional distance ladder. The cosmic microwave background provides another deep anchor. Its tiny temperature variations show the early density pattern from which later structure grew. Detailed maps of this radiation help fix the parameters of the standard cosmological model, including the amount of ordinary matter, dark matter, and dark energy. These early universe measurements can be compared with distances measured from Cepheids, supernovae, and galaxies in the nearby universe. The agreement is strong enough to give confidence in the broad scale of cosmic distances, but not perfect enough to remove all tension. The most important present disagreement is the Hubble tension. Measurements based on the early universe give one value for the current expansion rate, while measurements using the local distance ladder give a different value. The difference is not large in everyday terms, but it is larger than expected from the stated uncertainties. It may point to hidden systematic errors, or it may point toward physics not yet included in the standard model. For intergalactic distances, this tension matters because the expansion rate sets the scale by which redshifts become distances. The ladder is reliable, but it is also still being refined. That is the honest scientific position. The universe is not measured by one perfect instrument. It is measured by overlapping evidence nearby geometry, pulsating stars, stellar explosions, stretched spectra, ancient radiation, and large-scale patterns in galaxy positions. Each method has limits. Each also checks the others. Together they make the distances between galaxies not merely imaginable, but testable. The result is a map built from light that has travelled for years, millions of years, and billions of years, carrying small measurable changes across nearly empty space. To measure the unreachable is to accept that distance in astronomy is never only distance. It is brightness, motion, spectrum, history, expansion, and uncertainty held together carefully enough for the larger spaces to become known. A galaxy's surroundings can decide much of its future. The same kind of spiral system may continue forming stars for billions of years in a quiet region, or it may lose its gas after entering a dense cluster and gradually become redder, smoother, and less active. This is not because the laws of physics change from one place to another. It is because the conditions around the galaxy change. In the cosmic web, address becomes environment, and environment becomes history. A galaxy in the local group lives among a modest number of neighbours, with enough gravitational interaction to matter over long timescales, but not enough to strip away its structure all at once. A galaxy in the centre of a rich cluster occupies a very different setting. It moves through hot plasma shared by the whole cluster, passes near many other galaxies, and feels a strong collective gravitational field. A galaxy in a void may spend most of its life far from major encounters, evolving with a slower supply of disturbances. These differences show that intergalactic distance is not only empty separation, it helps determine how strongly galaxies affect one another, how much gas they keep, how often they merge, and how long they remain able to form new stars. The clearest example comes from galaxy clusters. A spiral galaxy entering a cluster carries its own supply of cold gas, the material needed for future star formation. In isolation, that gas may settle into the disk, collect into clouds, and form new generations of stars. Inside a cluster, the galaxy moves through the intracluster medium, the thin but very hot plasma spread between the cluster's galaxies. Although this plasma is sparse, the galaxy moves through it at high speed. The pressure created by that motion can push against the galaxy's gas. This process is called ram pressure stripping. It can remove cold gas from the outer disk first, then from deeper regions if the pressure is strong enough. Stars are mostly unaffected directly because they are compact and widely separated, but the gas is easier to displace. Once the gas is removed, the galaxy loses its main supply of future star formation. The existing young blue stars continue through their short lives and fade. Older, redder stars remain. Over time, the galaxy changes colour and activity. It becomes less like a star-forming spiral and more like a quiet system dominated by aging stars. The transformation does not require a single violent collision. It can happen through sustained motion in a dense environment. This is one reason clusters contain many red elliptical and lenticular galaxies, while isolated regions contain more blue star-forming spirals. The difference is not always birth. Often it is later treatment by environment. Cluster galaxies also experience tidal forces from the cluster as a whole and from close passages with other galaxies. A fast encounter may not lead to a merger, because relative speeds inside clusters are often too high for two galaxies to capture each other easily. But repeated near passages can disturb stellar orbits, thicken disks, pull out streams, and heat the galaxy's structure dynamically. Over time, this process can reduce the ordered rotation that defines a clean spiral disk. In the densest cluster regions, galaxies may lose stars into the shared cluster environment. These stars become intra-cluster light, a faint diffuse glow not bound to any one galaxy, but to the cluster's gravitational field. This light is difficult to detect because it is spread thinly across large areas, yet it records the long history of interactions inside the cluster. It shows that the space between galaxies is not always empty even in terms of stars. Some stars have been pulled from their original galaxies and now move through the cluster as part of a wider structure. The same environment that strips gas can also redistribute stars, leaving behind a record of gradual gravitational disruption. In smaller galaxy groups, the pace is different. Relative speeds are lower, and mergers are more likely. The Milky Way and Andromeda are an example of this kind of future. They are not in a rich cluster, and they are not rushing through a massive intracluster medium dense enough to strip them in the same way. Instead, their long-term evolution is shaped by mutual gravity inside a bound group. When galaxies merge in groups, gas can be compressed, star formation can be triggered, and stellar orbits can be rearranged into a larger combined system. Smaller satellite galaxies may be stretched into streams, absorbed gradually, or have their gas removed by interactions with the larger galaxy's halo. The Milky Way's own halo contains such remnants, showing that even a relatively quiet galactic environment is not free from change. The difference is scale and frequency. A group provides fewer major encounters than a cluster, but the encounters that occur can be slow enough to reshape galaxies deeply. The environment is less crowded, yet still active across cosmic time. In voids, galaxies experience another kind of history. Cosmic voids are not perfectly empty, but they are underdense. Large galaxies are rare there, and strong interactions are less frequent. A void galaxy may continue forming stars from its remaining gas, with fewer interruptions from major mergers or cluster effects. Many void galaxies are smaller, bluer, and more gas-rich than galaxies in dense regions. Their evolution can appear delayed compared with cluster galaxies, not because they formed outside time, but because their surroundings did less to accelerate transformation. A void protects by distance. It reduces the number of close encounters, weakens environmental stripping, and allows some galaxies to preserve gas reservoirs for longer periods. This quietness does not mean void galaxies are simple. They still rotate, form stars, accrete gas, and respond to dark matter halos. They still belong to the cosmic web, often lying along thin filaments that pass through void regions. But their address gives them a slower, less interrupted path. In that sense, the void is not merely the absence of galaxies. For the galaxies that do exist inside it, the void is a condition that shapes their lives. There are also objects that leave galaxies almost entirely. Some stars can be ejected through close gravitational encounters, especially near massive black holes or during complex interactions in dense systems. If a star gains enough speed, it may escape its galaxy and travel through intergalactic space. These hypervelocity or unbound stars are rare, but they show that even stars are not always permanent residents of galaxies. A star moving between galaxies would carry any tightly bound planets with it, if such planets survived the event that ejected it, a planet without a nearby star, or one bound to a star drifting far from any galaxy, would exist in an environment unlike the one that shaped Earth. The sky around it would have no dense field of nearby stars. Galaxies would be distant systems rather than a surrounding home. Such cases are uncommon, and no claim about life in such settings can be made without evidence. Their importance here is simpler. They show that the boundary of a galaxy is not absolute for every object. Gravity can remove stars, scatter planets, and place material into the spaces between larger structures. Most stars remain in galaxies, but some trace the pathways by which galaxies lose pieces of themselves. Intergalactic distance therefore affects galaxies in more than one way. It separates them, but it also regulates contact. Shorter distances in groups allow mergers and tidal distortion. Dense cluster environments add hot gas, fast encounters, and strong stripping. Large void distances reduce encounters and preserve slower evolution. The same basic ingredients, stars, gas, dark matter, and gravity, produce different outcomes depending on where a galaxy sits in the web. This is why large surveys do more than count galaxies. They reveal patterns in galaxy color, shape, star formation, gas content, and clustering. Red quiet galaxies are more common in dense environments. Blue star-forming galaxies are more common in less dense regions. The correlation is not perfect, because each galaxy has its own mass, merger history, and internal processes, but the environmental signal is strong. Address does not determine everything, yet it changes the range of likely futures. The Milky Way's own address is moderate. It is not isolated in a deep void, and it is not inside a rich cluster core. It belongs to a small group, near larger structures but not swallowed by them. That setting has allowed the galaxy to keep forming stars over billions of years while also absorbing smaller companions and preparing for a future merger with Andromeda. Its history is neither untouched nor heavily processed by a cluster. It is a middle case, shaped by neighbours but not crowded by 1,000 major galaxies. Seeing this helps correct the idea that galaxies are self-contained islands evolving alone. They are systems with internal physics, but their surroundings matter. The distance to the next galaxy, the density of the region, the presence of hot plasma, the speed of encounters, and the pull of the larger web all become part of the story. Place becomes destiny only in a measured sense, but that measured sense is enough. Across the universe, galaxies carry the marks of where they have lived. The present universe occupies a rare observational interval. It is old enough for galaxies, clusters, superclusters, and the broad pattern of the cosmic web to have formed, but not so old that accelerated expansion has carried most of that pattern beyond detection. This timing matters. If the universe were much younger, the large-scale structure would be less developed, and many mature galaxies like the Milky Way would not yet exist in their present forms. If the universe were vastly older, distant galaxies would be more strongly redshifted. Many would be beyond any future signal exchange, and the evidence for the wider cosmic web would be reduced. The present era sits between those limits. It contains mature structure and still allows that structure to be observed across enormous distances. This does not make the era central or special in any absolute sense. It only means that the conditions for cosmic measurement are unusually informative. Light from nearby galaxies shows the current local universe. Light from distant galaxies shows earlier stages. The cosmic microwave background shows the early pattern from which structure grew. Together, these signals allow a long history to be reconstructed from one location in space and one moment in cosmic time. The scale that emerges is larger than the local sky suggests. The Milky Way is a spiral galaxy about 100,000 light-years across. Its nearest large companion, Andromeda, lies about 2.5 million light-years away. The local group spans roughly 10 million light-years. The Virgo region lies tens of millions of light-years farther out. Laniakea extends across hundreds of millions of light-years. Beyond that, other filaments, clusters, walls, and voids continue outward to the observable horizon, about 46.5 billion light-years away in every direction. These distances are not simply larger steps on one ladder, they are changes in regime. Inside a galaxy, matter is concentrated enough to make stars, planets, gas clouds, and chemical cycles. Between galaxies, matter becomes thin. Between clusters, it becomes thinner still. Across voids, galaxies can be rare over spans that make even the local group seem compact. The visible universe is therefore not mostly made of bright systems. It is mostly volume between them. The luminous structures are essential, but they occupy only a small share of the space available. This is the quiet fact behind the distance between galaxies. The universe is not crowded at its larger scales. It is structured, but structure does not mean fullness. It means that matter has gathered into certain regions, leaving much larger regions underdense. The most distant observable galaxies add another layer to this picture. Some are seen as they were when the universe was only a few 100 million years old. Their light has crossed almost the whole history of cosmic time before reaching modern instruments. During that journey, space expanded, so those galaxies are now far beyond the simple travel time of their light. They're part of the observable past, not the reachable present. This distinction gives deep astronomy its strange precision. Telescopes can measure objects that no signal sent now from those objects will ever deliver in a form connected to their current state. The observation is real, but it is also historical. The more distant the galaxy, the older the light, and the more expansion has altered the separation. In this way, the distance between galaxies is also a distance between eras. A nearby galaxy shows a more recent stage. A distant galaxy shows a younger universe. The cosmic web itself is observed not all at once in a single present, but along a light cone, with farther regions seen further back in time. The map of the universe is therefore partly a map of history. This is not a limitation that can be removed by better technology. It follows from the finite speed of light. Better instruments can sharpen the record, detect fainter sources, and separate finer details, but they cannot make distant light arrive without travel time. The delay is part of the information. It allows the universe to be studied across age, but it also prevents any direct view of distant regions as they are now. Accelerated expansion makes that separation more permanent. In the far future, observers inside the merged remnant of the local group will not have the same sky available. The galaxies that now define the larger cosmic web will have faded beyond practical detection. Their light will be stretched to wavelengths too long and too weak to preserve an accessible record. The cosmic microwave background will also be stretched and cooled until it becomes far harder to measure. The universe will still contain more than the local remnant, but the evidence for that wider reality will be hidden by distance and expansion. A future civilization, no matter how patient or advanced, could look outward and find a universe that appears almost empty beyond its own galaxy. It might infer some things from local dynamics and relics, but it would not have the rich external evidence available now. This gives the present era a scientific value that is easy to overlook. Cosmology is possible in its current form because the universe has not yet erased too much of its observable record. The galaxies remain visible, the background radiation remains measurable, the expansion remains traceable through redshift. The arrangement of matter still carries the imprint of early conditions. That record will not remain equally accessible forever. The thought is not dramatic in a physical sense. It is gradual, governed by ordinary cosmic expansion, acting over immense time, but its consequence is clear. Distance will become a stronger form of separation than it is now. What is remote today will become unobservable later. What can be mapped today will eventually leave no direct signal. The universe does not have to disappear in order to become unavailable. It only has to keep expanding. The final perspective, therefore, is not that galaxies are merely far apart. It is that their separation defines what can happen, what can be measured, and what can ever be known from a given location. Distance determines whether gravity binds or expansion wins. It determines whether galaxies merge or recede. It determines whether light arrives with useful information or is stretched beyond recovery. It determines whether the cosmic web is visible as a connected structure, or reduced to a local remnant. The same distance that makes Andromeda faint also makes the far universe historical. The same expansion that enlarges the observable scale also closes future access to many of the objects now observed. Intergalactic space is therefore not an empty stage around galaxies. It is part of the physical story. Its size, density, expansion, and hidden matter shape the entire interpretation of the cosmos. From inside the Milky Way, the first impression is a sky of stars. Measurement replaces that impression with a larger and more careful view. The stars belong to one galaxy. That galaxy belongs to a small group. The group lies within broader flows. The flows trace a web whose largest regions are voids. The web extends to a horizon set by light, time, and expansion. Beyond that horizon, the universe may continue, but not in a way that can be directly observed from here. The result is neither simple emptiness nor simple abundance. It is an uneven universe, rich where matter has gathered, sparse across most of its volume, and changing as space expands. The distance between galaxies is bigger than intuition expects because intuition was formed inside a galaxy, near a star, on a planet. Within a dense local environment, the wider universe does not share that density. Most places are not like the night sky as seen from Earth. Most places are between the bright structures, not within them. Recognizing this does not require exaggeration. It requires allowing the measurements to remain what they are, millions of light years to the nearest large neighbor, tens of millions to the nearest major cluster, hundreds of millions across local supercluster scale flows, and tens of billions to the observable boundary. Each number marks a real separation crossed only by light, and even light is limited by time and expansion. The present era still receives enough of that light to assemble a coherent picture. It is a temporary advantage built into cosmic history. For now, the sky contains nearby stars, neighboring galaxies, distant clusters, early galaxies, and the ancient background radiation. The record is incomplete, but it is broad enough to show the shape of the larger universe. Across future ages, that breadth will narrow. The local remnant will remain, but the wider evidence will fade. The last visible era is not an ending. It is the current interval in which the universe is still open enough to reveal much of its own structure. The distance between galaxies is the measure of that openness, and also the reason it cannot last without limit. Across every scale, the same quiet pattern remains. Matter gathers where gravity can hold it, and between those gathered places space opens into distances that no ordinary experience can prepare the mind to hold. A galaxy feels immense because it contains stars, gas, dust, black holes, and the long record of its own formation. Yet even a galaxy becomes small when placed beside the gaps that separate one system from another. The nearest large neighbor is already millions of light years away. The nearest major clusters lie much farther still. Beyond them, the cosmic web continues through filaments and voids, visible now because light from many eras is still arriving. That light carries the evidence of expansion, of early density patterns, of dark matter's hidden structure, and of ordinary matter spread so thinly that it can be found only through careful traces. Nothing in this picture needs to be made larger by language. The measurements are already enough. They show a universe where brightness is local, emptiness is vast, and distance is not only separation but history. The present sky still holds a rare record nearby stars, neighboring galaxies, distant clusters, young galaxies, and the cooled radiation from the early universe. In time, expansion will narrow that record. More of the universe will pass beyond future reach, not by vanishing, but by becoming unable to send new light across the growing space between. For now, the evidence remains open. The Milky Way still sits within a wider map. Andromeda still shines faintly across its long gap. The background radiation still carries its ancient pattern. The distances between galaxies remain difficult to imagine, but they can be measured, followed, and understood with care. In that careful understanding, the universe becomes neither less mysterious nor more exaggerated. It becomes clearer, quieter, and larger than intuition once allowed.